Hi everyone, in this video I'm continuing to work through question 14 part E of the 2020 Extension 2 trial exam from Sydney Boys High School. So I've just worked through part 1 in a prior video, so definitely have a look at that if you haven't already. Here in part 2 we're being asked to show that the complex number represented by D on the Argand diagram is equal to the square root of 2 capital R squared minus 2 times lowercase r capital R. So the square root of all that, all multiplied by e to the I times theta on 2. And so again, that's in terms of lowercase r, capital R, and theta. Now here I think we're actually given the thing we're working towards here. So in part 1 we were just told to find the complex number for b, but not actually told what it was. Here we're given a bit more of a steer, and actually through working through this part 2, again, thinking about it in terms of an exam, you kind of almost get to find out whether you got part 1 right. Because I guess if you can't get to this result here in part 2, one possible explanation is that you didn't get the right result in part 1. So you could probably have a crack at this question, and if you find that you're not getting anywhere, maybe part of what you'd have to do in an exam is go back and revisit part 1. But on the other hand, if you do work through part 2 and get this result, you can almost guarantee that you've probably got part 1 right as well. All right, let's dive in and have a look. So here I've just written out what we're being asked to show, because we're actually given the result that we want to show this time. So just like before, I'll get my trusty electric socket tape and I'll just draw up this diagram. One day I will buy a compass, but actually I find this socket tape is actually the perfect size for drawing the kinds of circles I need to answer the questions I come across. So here we go again. Once again, the outer circle touches the real axis at the origin, so I'll just draw up my axes here. So we'll have the real axis going along here, so that's real. We have the imaginary axis going up, so that's imaginary. Now in terms of the key points, again I'll just try and make sure that my center is somewhere reasonable, so we'll call that C for the center of both of the circles. We had our tangential line, so if I just note these points, so A will be the point at which OB is a tangent to the smaller circle, so let's draw that on. We had then, as C goes through A, that I believe this was dotted, that got us to point D, and D is what we're concerned with here. What is the complex number for D? And we worked out, and I'll throw that on too because I think that was in the question. We were told this was theta. We worked out that CAO is a right angle, and now we're looking for D. Now, just like we did in part 1, we're starting from the idea that the complex number in exponential form will be, and maybe I'll just throw on, maybe I'll use black. I'm just going to throw on the line OD, and this diagram starts to get quite a bit going there. So D as a complex number will be equal to the magnitude of OD, the modulus, so I'll just write that as OD for now, times e to the I, and basically this angle here, which I'll just call gamma. Theta, I'll call it gamma, which is this angle here, so e to the I gamma. And really from there, the question then becomes, we need OD and gamma in terms of lowercase r, uppercase r, and theta. But more specifically, because we're told the result we're working towards, actually what this means is we know OD will line up to this. We need OD to be equal to the square root of 2 capital R squared minus 2 times lowercase r capital R. And we need gamma to be, we need to be able to show gamma is theta on 2. Because actually, if we can show those two things, when we plug them into our exponential form, we get the result that we're being asked to work towards. So that's the challenge. As I mentioned in the last video, just like it was with part 1, actually a lot of the effort is related to using what we know about trigonometry. So in part 1, it was essentially making use of Pythagoras' theorem. I actually think here in part 2, it's also Pythagoras' theorem again, largely. But there's just a whole lot more triangles that we've got to try and work with and just be careful not to mess up. Now, I think one of the triangles that I think are going to help us is triangle OAD, this triangle here, which, again, if we know this is a right angle, we also know this is a right angle. So it's a right-angled triangle. Now, in part 1, if I just flip back to my working in part 1, we worked out the length of OA. That was something we had to do to get part 1 working. So we know the length of OA. And do we know the length of AD? Well, we kind of do, because we know that the radius of the big circle is R, and we know that the radius of the the big circle is capital R, and the radius of the little circle is lowercase r. So AD is just a difference between those two radii. And so that's going to be enough with Pythagoras to get us OD. So what I might do is I might just draw up this triangle. So let's start by saying, let's consider triangle OAD, and I'll just draw it up so that we can kind of annotate it without all the noise from the rest of the diagram. So if I put the right angle here, then this point would be A. This point here would be D, and this point here would be O. And as I mentioned, OD is what we're looking for. OA, we know from part 1, is the square root of capital R squared minus lowercase r squared. So this is the square root of capital R squared minus lowercase r squared. And a dA will be capital R minus lowercase r. It's the difference of the two radiuses. So again, just like part 1, we can say by Pythagoras, and now we just apply Pythagoras' formula. So OD squared, the hypotenuse squared, will be the sum of the squares of the other two sides. So the square root of r squared, capital minus lowercase r squared, all squared, plus capital R minus lowercase r squared. So that's going to be, this square root will disappear when we square it. So we get capital R squared minus lowercase r squared. And here I'll just expand. So we'll get the first one squared minus twice the product plus the last one squared. And this minus r squared and plus r squared will cancel. We've got 2 of the capital R squareds. And then we've got a minus 2 lowercase r capital R. And we want OD, just OD, so we get OD is equal to the positive square root, because it's the length, of 2 capital R squared minus 2 lowercase r capital R. And that is exactly what we needed to show for OD. So there you have it. We're kind of halfway through. We've worked out OD in terms of what we had to. Now we've got to focus on this angle gamma. And here again, I think it's about strategically picking what triangle we want to deal with. Now here actually I think what will help us is if we extend this line CD all the way to the axis, and maybe I'll call that point where that line hits the axis E. I think we can work with this triangle ODE. Now there's a little bit we need to do first, but maybe I'll annotate this main diagram in red, because if we can find this angle here, and if we can find this angle here, then we will be able to use this angle sum of a triangle to find gamma, which is what we want. So we need each of these angles specifically in terms of theta, and then we'll be ready to roll. Now, I think using all of these triangles in here, we can kind of piece everything together, because what we can say right away is this angle here, we know is, well, that's a right angle, so this is 90 minus theta. And because this triangle OAC is a right angled triangle, that angle sum will be 180. So this angle here will be 180 minus 90, which is 90, minus 90 minus theta, which would then end up just with theta. Okay, now noting that this big triangle OCE is a 90-degree triangle, this angle E would be 180 minus 90, which is 90, minus theta. So this angle here actually becomes 90 minus theta. And now if we can just find this angle in here, we've got everything we need. And I think that angle, what's going to help us is this triangle COD. Now what I might do, I might turn over, and maybe whilst I've annotated that, in terms of the working you might want to show to be complete, we might say something like, maybe I'll say, let's start by saying, just writing out what we've just shown. So angle AOC is equal to 90 minus theta. And then we say angle OCA is equal to theta. So therefore angle OCA is equal to theta, and that's through the angle sum of a triangle. And therefore we say angle CEO is equal to 90 minus theta. Therefore angle CEO is equal to 90 minus theta, and that's also angle sum of a triangle. And now we want to focus on angle ODE, but before we can do that, it's actually, all we really need to do is find this angle, and then it'll be 180 minus this angle here. So let's work through this. I might have to just draw a separate triangle. Things are getting pretty crowded here. So let's consider triangle OCD. So let's consider triangle OCD, and I'll just draw that up. Now this won't be a right angled triangle, but that's okay, because I think there's another rule of trigonometry that we can make use of. So let's just make sure I label these points correctly. So we're going to have OCD, so I'll call this OCD. And we've just worked out that OCA, which is again the same angle as OCD, is theta. So we're using what we just worked out. Now, we know that the length of OC is capital R, it's the radius. We also know that the length of CD is capital R because it's also the radius of that same circle. So therefore, if these two sides are equal, we know that these two angles are equal. And then using the sum angle of a triangle, we can work out what they are. Maybe I'll just call it x for now, just as an unknown. So we can say, since triangle OCD is isosceles, angle COD is equal to angle CDO, and we're just going to call it x. So you can say, therefore, theta plus x will equal 180. So 2x will equal 180, and I'll bring the theta over. Therefore, x, that angle, is 180 on 2, which is 90, minus theta on 2. And that's kind of a good sign because we know we're going to want a theta on 2 eventually. So coming up with the theta on 2 is very handy. So we've got this angle here as being 90 minus theta on 2. Maybe I'll just annotate that on. So that's 90 minus theta on 2. So now we can work out angle ODE. So we can say, therefore, angle ODE is equal to 180 minus 90 minus theta on 2. And so that's going to be 180 minus 90 plus theta on 2, because the minus and minus gets us to a plus. So 180 minus 90 is 90, so we're going to get 90 plus theta on 2 for our angle ODE. And now we can consider our final triangle. Let's consider this triangle ODE. So it's the last triangle, so it's the third triangle, although we've actually been looking at a lot of triangles here. But let's consider triangle ODE. So let me just draw that up. We've got ODE, yeah. So we'll just draw it up like this. Just lengthen that a little. So we'll have ODE. Now remembering that angle DOE is gamma, so angle DOE is gamma, that's what we're most interested in. Angle ODE we just worked out as 90 plus theta on 2, and angle angle DEO, which I don't, yes, we worked that out, angle DEO, angle DEO, we actually worked out as angle CEO, but it's the same angle. That's the 90 minus theta, so 90 minus theta. So we can say gamma plus 90 plus theta on 2 plus 90 minus theta will be equal to 180. That's angle sum of a triangle. Now these two 90s and the 180 all cancel. And we can bring, we can basically keep our gamma here, and we'll bring over the theta, and that'll become plus theta, and then minus theta on 2. And theta minus theta on 2 is just theta on 2. So gamma is theta on 2, and again, that's what we're after. So we've got our two ingredients, now we can put them back in. So we can conclude now, maybe I'll just put it right here, therefore the complex number D is equal to OD, which we worked out as the square root of 2 capital R squared minus 2 lowercase r capital R, e to the I gamma or theta on 2, and that is as required. That's exactly what we were being asked to show.
Sonic boom!
Alright, so there you have it with that question. Tricky one. I think the essence of this question isn't really all the complex number stuff. As long as you know the exponential form of a complex number, that's kind of where it ends in terms of making use of complex techniques. The rest of it, as you saw, was just being strategic about picking relevant triangles to then work out various things. First, we picked OAD to get the length of OD using Pythagoras. Then we did a bit of work around angle sum of triangles and, you know, the difference between a right angle or a straight 180 degrees to get all our various angles to eventually work out gamma, plug it into the exponential form, and job done. So hopefully that's all made sense for you. I think it is certainly a tough question to have to face in an exam. I think a I think where a lot of students might struggle is they might get a bit overwhelmed with all the information thrown at them in this diagram. And also, there's a little trick to it, I guess, because you might be inclined to think this is a complex number question. What complex number techniques do I need to use? But as you see, it's mostly just basic trigonometry. So, yeah, it takes a lot of just kind of thinking methodically and I guess being calm all the way through to just really notice that actually this is a trigonometry question at the end of the day. So yeah, there you have it, and tick boom.